continue where we left off. We'll just see the solution of the resizing array problem that I left you on. So the question was, if we reduce the size with pop back of the new vector, what is the ideal length to do so? And the answer is, when the vector is n by 4 filled, you have to reduce it by half the size. Now why is that? Now, when you reduce it n by 2, when you reduce it to half size, when it is exactly at half size, what happens when you need to push back again? The vector has to double, that takes an on. Now you have to pop back again. Now there has to be a shortening again. And so every pushback and popback operation that happens at that point will have an expected complexity of order of n, not an asymptotic complexity of order of 1, which is a problem. N by 4, what does that result in? It says at any time the vector won't be more empty than 75%, and there will always be space to keep something, which sounds very nice. Not reducing is optimal in many cases where you do not care too much about the memory and you know there is not going to be too many entries, but it is always advisable to reduce the size. And now, since this is done, let's go to the time complexity analysis as well. What is asymptotic analysis? Asymptotic means tending to infinite. When the size increases, when we take our calculations to the infinite, it is known as asymptotic analysis. And let's talk about our vector. When does the size increase? The size increases at points 2, 4, 8, 16, 32, 64, 128. So all of these are log to the base 2 points, which means they are powers of 2. So the best case performance occurs between these ranges. So when the 13th or the 14th element or the 18th element is pushed, it is just written into that space, which is an order of 1 complexity. But the worst case is when at these numbers 2, 4, 8, 16, etc., the vector size has to double and we have to copy all these elements over. This is an order of n complexity. But what is the average case complexity? Now let's see, let's say we have pushed 10,000 elements. How many times did we need to do a very huge operation? It is only 14 times. And 14 times you're doing very large operations, and the rest of the time you are doing unnoticeable operations. So that makes the time complexity an asymptotic order of 1, because when you go to infinite, the log of infinite, that is the number of times the expansion has to happen, that will be very less compared to the number of operations that are done in a very low order. I think that this clears it up. So every pushback operation on an average takes an order of 1, but in certain very unlikely worst cases, it does take an order of n. This was the time complexity analysis of this program.